this video, I'm going to show you what is the principal components analysis, PCA, and how to apply PCA to a specific data set using machine learning. So a PCA is an unsupervised machine learning technique that pretty much reduces the dimension of your data. Say, for instance, you have 1,000 features that you want to be able to make sense of it, and you can't use all of them, right? So you have to reduce them to maybe the best two, the best three, or whatever that is. So PCA is used for that purpose. What it's going to do is going to combine the 1,000 features into two or three components, and those components will not compromise, at least not compromise completely, the information that those 1,000 initial features had in the data. So it's definitely a dimensionality reduction a feature, and is used most of the time for clustering. Now, there is no target variable. There is no response, no label, or anything like that. That's why it's called unsupervised. So here are the steps. The first step is to have the data standardized, meaning that you want to have all the values at the same scale, which is definitely necessary when it comes to machine learning and have a good training model. The second step would be to construct a covariance matrix, and we're going to get to the definition of covariance next. The third, once you have the covariance matrix, you do a decomposition of that matrix into eigenvector and eigenvalue. Next, you derive the eigenvector from the eigenvalues, looking at the k largest eigenvalue. Why? Because the largest eigenvalues are the ones that will give the best explanation of the data. Okay, so take the eigenvectors are the best eigenvalue that you can get from your data. And finally, you construct a projection matrix. All this is done in scikit-learn, where you have your finite dimensions for step 5 and 6. Now, if you want more detail about the steps and how to construct those out of scratch, I will have a separate video for that. But for now, let's go over a few definitions. What is covariance? So covariance starts with the definition of variance itself. Variance is how dispersed your metric or your variable is from the mean. It's a measure of it's a measure of dispersion. Now, there are ways to measure the variance between two variables, which is covariance, or in other words, how much information those two variables share with each other, right? So if you have three variables, then you have a three-dimension covariance. An eigenvector is the principal component itself, which is the reduced dimension of the 1,000 initial feature example that I gave you. It's based on the most powerful eigenvalues, which are the most explained variance eigenvalues, and it's a pretty final version of your eigenvalues, final and best version of your eigenvalues. Now, this is a high-level explanation of what PCA is, and for this lecture, I just want to show you, after the explanation, how you can apply this to any dataset that you have. So we first start with importing the necessary package. I have NumPy for the linear algebra, and then I have all the scikit-learn that I need. Okay, and I will have a linear logistic regression to kind of see if the PCA is working properly as expected, because there will be a separation of my data points. Okay. All right. Let's get started. So here I import the data. The wine data will be the example, and you can see that I have 13 features. I have 13 features. I want to reduce those 13 features to maybe 2 features, and this example is going to be 2. All right. You can see that the values are not scaled properly, because you have the last column 13 has 1065, 1050, and stuff like that. But in comparison to other columns, which are pretty small, you can see that I can tell that the model is not going to fit well. So it's necessary to have a standardized process to capture or to rescale my data. Okay, so I derive my matrix here, and then I separate my y, and then here I split my data set into training and testing, which may not be necessary for this exercise, but this is best practice. And you can see here that I do my transformation using the standard scatter from scikit-learn. Now, from there, what do I do? I have my covariance matrix that I can derive from my training set. Okay, and from here, I can quickly derive my um, eigenvectors and eigenvalue, because if you remember, we can break or we can decompose the covariance matrix into eigenvectors and eigenvalues. Scikit-learn does that perfectly. All right, now that I have my eigenvalues, this is the vector of eigenvalues. Now, what do we go? Where do we go from there? Well, the eigenvalues is what give us the variance explain, the explained variance. Okay, I mentioned that earlier here. You can use it to calculate the proportion of variance represented by each eigenvector. Now, um, how do you do it? You take one value and you divide by the sum of all the eigenvalues. That's pretty much what I'm doing here. Okay, take each eigenvalue and divide by the total, and then the eigenvector will be the best eigenvalue, and that's what I'm seeing on these plots. You can see that the first principal component here is explaining close to 40% of the whole data, right? The second two, and these are pretty much eigenvalues, the best eigenvalues. The first and second eigenvalue both explain about 60% of all the 30 features. So this is to say that once I have my best eigenvalues, I can use these as my eigenvectors, depending on the level explanation of my eigenvalues. Because you can see here that they have been sorted in descending order, right? So this is a nice chart to kind of explain the variance ratio. Now let's go further and see how we're gonna get these two components that explain the variance well on the data, and see how they work as far as separating the data points. So here I have a plot decision region which look pretty neat, and really what I'm doing is I'm taking the two eigenvectors. Okay, I'm taking those two eigenvectors, and I am feeding a logistic regression on top of it, um, where I can show you here. I can show you here the details. So I have these are my two eigenvectors that I was showing you earlier. I fit a logistic regression that I pass into the data, okay? And then here's my classifier. I have um, my X inputs, my matrix input, and then I have Y. Now we talking about logistic regression here that has nothing to do with PCA. I'm just trying to separate my data point using logistic regression and see if the PCA that I have done is working well. That's pretty much what I'm trying to do. So I have my two dimensions here, but here you can see how the PCA has been able to separate properly my data points. Because here I have a kind of three level, the target or the response variable has three different classes. Um, I can see that the PCA is working well in this specific scenario. So meaning that my PCA is working pretty correctly. So this is how we use PCA. PCA is used for clustering purposes most of the time. And when you don't want to do a cluster on so many features, right? So you just want to do about two features. You can use PCA first to reduce your feature into a few ones, and then do a cluster on top of it. So yeah, if you like this video, give me a thumbs up, and don't forget to subscribe to my channel. I hope you like this video. This was a brief and short explanation of what PCA is. I will have the notebook share on my the GitHub link that I will post at the bottom of the video, and I will also have this on my blog.